Welcome back to structural dynamics class. So in this module we will study about dynamic amplification factors. So last class we have studied about damped forced vibration and undamped forced vibrations. So as we have noticed in that is when forcing frequency and the natural frequency of the system matches, a resonating condition is taking place. So in this resonating condition, amplitudes of displacement, amplitude of velocity and amplitude of acceleration will go to very high values. So sometimes up to infinity or very large values. So because of the presence of damping, we can reduce this amplitude to a greater extent. But let us understand the relationship between this dynamic amplification factor for displacement, velocity and acceleration in this class. So how they are sensitive to frequency ratio and like where do we apply, all those things we will study in this class. So the outline of this class is dynamic response factor for displacement we will understand, response factor for velocity we will understand, dynamic response factor for acceleration we will understand. We will try to derive the relationship between these three factors: displacement, response as well as acceleration. Now if we look at the equation of motion, so which consists of three terms, that is inertia term, damping term and stiffness term. So all these added together is equal to the external force which is dynamic in nature. P0 is the amplitude of the force and omega is the forcing frequency. Now if we look at the steady state amplitude which we have understood in the last class. So steady state amplitude is the product of static displacement and dynamic amplification factor for displacement as well as the sinusoidal component. So in this we need to observe the presence of this phi. This phi is a phase angle. So phase angle means like the way the force is getting applied and the way displacement is taking place. So are they in phase or are they out of phase? So in phase means when we apply force, displacement also will be in the same direction. But out of phase means when we apply force, displacement will be in the opposite direction. So these conditions also we will try to understand in this one. Now if we look at this one, so dynamic displacement divided by static displacement is equal to Rd multiplied by sine omega t minus phi. But if we take only amplitude, it becomes this much portion amplitude. So this Rd is called deformation response factor or dynamic response factor for displacement. So it is a ratio of U0, that is amplitude of dynamic deformation, to static deformation. So we know that static deformation can be found out by amplitude of the load divided by stiffness. This is static deformation. So dynamic deformation, is it more than the static deformation, less than static deformation? So what are the cases which increases, decreases this dynamic deformation compared to static deformation? We will try to understand. So now if we plot this curve Rd, so that Rd is U0 by UST, and this Rd is, the equation is 1 by under root 1 minus zeta square plus 2 zeta r, sorry 1 minus r square, 1 minus r square plus 1 minus r square whole square plus 2 zeta r square. So if you substitute r in this one, r value from 0 up to say 2.5, will get this response. So this response is for different damping values. So this first, this one is zeta value is equal to 0 and here zeta value is 0.1, 0.2, 0.7 and zeta 100% damping. As you can see in this curve, we can see that at when r is equal to 1, in this if I substitute r is equal to 1 and when zeta is equal to 0, so this term will disappear and we will be left with only 1 minus r square. When r is 1, this will become 0. So that means the amplitude of Rd value will be infinity. And when we introduce say 10% damping, 20% damping, something like that, so suddenly this amplification, the peak value it is getting reduced. This is dynamic amplification factor for displacement. Now dynamic amplification factor for velocity. So as we know, this is the equation. So u dynamic displacement divided by static displacement is equal to Rd multiplied by sinusoidal part, that is omega t minus phi. So if we differentiate this equation, then what we get is, so on the numerator we get velocity, and here if we differentiate, one omega comes out of that sin omega t minus phi, so omega, and cos t it will remain. So ust is nothing but p naught by k, amplitude by stiffness. So if we rearrange these terms and by dividing by omega n, so what we get is this omega by omega n will remain, and this p naught by k into omega n. So if we rearrange this one, omega n is under root k by m, we know omega by omega n is a ratio of frequencies. So r is equal to omega by omega n, it is ratio of frequencies. So we can write that u dot divided by p naught by under root km is equal to Rd multiplied by r into cos omega t minus 1. So what we can look at is, you can see this one u dot t. So u dot t means velocity, okay, in that, so this term can be treated as Rv. So this is called dynamic response factor for velocity. It is the ratio of amplitude of dynamic velocity to static velocity. It is like Rv. So dynamic velocity, and this is static velocity. So the graph, if we plot this one, the graph what we will get is like this. Okay, again in this one you can see when damping is not there, this values goes to infinity, and with the presence of damping the peak amplitude drastically reduces. And then in the similar manner, let us go further and analyze dynamic amplification factor for acceleration. So the same equation we take, but here now we will differentiate it twice. So if you do it twice, what we will get is u double dot on the numerator, and here if you look at this carefully, Rd multiply by, we need to do it twice, so omega square term will come. So one omega came down here, so another omega is remains here. You can see if we divide that by omega n, so what we get is u double dot p naught by under root km, again under root km because of omega natural frequency dividing by natural frequency, we get r square Rd sin omega t minus 1. So this negative sign can be removed because we are testing the amplitude only. So now u double dot by p naught by k, using this equation if we look at it, then minus r square Rd sin omega t minus phi. So in this one, so this term can be treated as Ra, dynamic amplification factor for acceleration. So Ra is acceleration response factor. It is a ratio of dynamic acceleration to static acceleration values. Now if we look at the plot of this dynamic acceleration, we get the similar plot, but there are some changes. I will explain these changes a little while later. Now if we look all three at a time, okay, so these graphs looks quite similar, but when we observe it, we will find the differences. So at r is equal to 0, r is equal to 0 means it is slowly varying force or static force at this location. When r is equal to 0, what is happening to Rd, Rv and Ra? Let us look at that. Rd is starting from 1, you can see this value is 1. So that means what? When the body, you can see this one, like let's take cantilever beam and a person or say a moving mass is moving weight is there. So if it is standing here, r is less means it is static. Static means directly deflection will be there. So ratio of static deflection to dynamic deflection is 1 only. So that is equal to static deflection again. And if you look at Rv, velocity, since there is mass is not moving, that force is not moving, Rv will be 0, and similarly Ra will also be 0. So at r is equal to 0, at lower frequencies or at rest condition, omega by omega n, that omega is 0 or nearly equal to 0, we get r is equal to 0. So Rd is equal to 1, Rv is equal to 0, Ra is equal to 0. When we go to extreme values, okay, or when we come to resonating frequencies, what is going to happen? Resonating frequencies along with damping, Rd is equal to Rd max value, so something like this at this location, and then RV is RV max and RA is RA max. So a point need to be observed in this one is all these RD max, RV max and RA max values, they are not occurring exactly at the same value, but they are nearly maximum at that value, nearly maximum. Because of the presence of damping, that slightly shifts slightly away from this one mark. And when R value is much greater than 1, so that means R is say 10, 20 something like that. So what happens is RD goes to 0. You can see here. So at larger values RD goes to 0 and RV also goes to 0 and then RA is equal to 1. So that means what we can clearly see that at lower values RD is sensitive, at higher values of frequency ratio RA is sensitive, and at resonating frequencies RV is sensitive. So if we look at the relationship among these three things, RA divided by frequency ratio is equal to RV, that is again equal to R into RD. Now let us look at some special cases in this. What are these special cases? Special cases is, if we discuss in detail, that is when R is equal to 0, that is at rest condition. So at rest condition, so if you look at this RD equation, RD is equal to 1 by 1 minus R square whole square plus 2 zeta R whole square. Now when R is equal to 0, if you substitute in this one, so what remains is, so all these values become 1. So RD becomes 1 and this phase is 0. So that means what, at rest condition or near rest condition, so when the forcing frequency is applied like this, so in the direction of force, displacement will be there. So that is what is the meaning of in phase, in phase. So phi is equal to 0 means in phase, and 5 is equal to up to 90 is in phase only. Then suddenly if it shifts and goes to 180, that is out of phase. Now if we substitute this value, what happens is RD is equal to 1. RD means U0 by UST, if it is equal to 1, then it gives us U0 is equal to UST. So that means what, UST, U0 is equal to P naught by K. So what we are understanding from this is, P naught is the externally applied force amplitude of externally applied force. Then K is the stiffness controlling. So that means what, K is stiffness. So when R is equal to 0 or nearly 0, vibration is controlled by stiffness. So that means stiffness controlling system it is. So if frequency ratio R is much less than 1, it is slowly varying force. RD is slightly larger than 1. So that means what, it can be 1, 1.01, 1.001 or 1.12, something like that. The system becomes independent of damping. Here damping has no role to play, whatever damping may be present in the system, but deflection is controlled by stiffness. So more stiff, less displacement, less stiff, more displacement. So this is first special case where force is slowly varying. And the second special case is when force is rapidly varying. So when force is rapidly varying means what, high frequency forces are acting on the system. When we look at the RD response curve, so 1 by under root 1 minus R square whole square plus 2 zeta R whole square. So that means what, R value is much larger. So if R value is much larger, the second term loses significance. So under root and square, that becomes only 1 by R square. So this is approximately equal to 1 by R square. If you put say numerical some numbers and you check, so you will get the similar value. Maybe you can put say R is equal to say 20 and check, approximately that will be same. You will get in this one, and zeta, any value zeta will become insensitive there, like 1 by R square. RD is equal to approximately equal to 1 by R square, and this shows that it is out of phase. So when R value is more than 1, vibration becomes out of phase. When R value is less than 1, vibration amplitude is in phase. It's something like when force is applied, force is applied, displacement is in the same direction. But when R value is very large, when force is applied, displacement comes like this. So it goes like this. Okay. Using this, RD is equal to 1 by R square relationship, as you can see. So this is equal to U0 by UST. So that means what, U0 is equal to 1 by R square into UST into 1 by R square. So that means 1 by R square means P naught by UST into 1 by R square. So UST is P naught by K, and if you expand this one, if you open this one, what is going to happen is something like this, P naught by K into 1 by R square, but that is equal to P naught by K into omega n square by omega square, omega n square by omega square. So P naught by K omega square into omega n square means under root K by M. K by M. So we will be left with P naught by M omega square. Oh, sorry, this n is not there. So P naught by M omega square. And if we look at this one, this is controlled by mass. So that means what system parameter is there in this one? Mass is there. So more mass, less amplitude, less mass, more amplitude. In the earlier case, more stiffness, less displacement, less stiffness, more displacement. That is a special case 1, this is special case 2. So in this one, what we can summarize is, the frequency ratio is much greater than 1, that is rapidly varying force, then already tends to 0, and it essentially unaffected by damping. So higher value means it is very less value, 1 by R square. For large values of R, vibration is controlled by mass. So mass control system, slowly varying force, stiffness control system, rapidly varying force, mass control system. Now let us look at the third special case. Third special case is when R is equal to 1. So that means what? When forcing frequency is very near to the resonating frequency. Okay. So if we look at this one and substitute R is equal to 1 here, so we will be left with 2 zeta. So RD is equal to 2 zeta. So that is nothing but U0 by UST. RD is equal to the ratio of dynamic to static displacement. So, and then phi is 90. So phase is exactly 90. Okay, that is the switching of location. So P naught by K 1 by 2 zeta. So here zeta is damping ratio, that means we can call it as vibration is controlled by damping. So if frequency ratio equal to 1, RD becomes very sensitive to damping, and for small values of damping, RD can be several times larger than 1, implying that dynamic deformation can be much larger than static deformation at this range. So as in summary, we have studied like RD, dynamic response factor for displacement, dynamic response factor for velocity, and dynamic response factor for acceleration, and how these three things are related, that we have studied in this class. And then in dynamic amplification curve RD, so at different places sensitivity we have studied. So when force is slowly varying, okay, so that means R value is near to 1, then deformation is controlled by stiffness, and when force is rapidly varying, then R value is very large, so that is rapidly varying force, deformations are controlled by mass. And then when R is around resonating frequency or around 1, that means forcing frequency and natural frequency are same, nearly equal, so then deformation is controlled by damping. So K control system, M control system, and C control system. So these three controls when they come into picture, so that we have discussed in this class.